In our work thus far, we've been concentrating on game players that process GDL directly during gameplay. This works reasonably well, as we've seen in the past, but we can do even better. As it turns out, it's possible to convert an arbitrary GDL game description into an equivalent propositional net. And then it's possible to use that propositional net to determine legality, update, termination, and so forth. Doing things this way is frequently more efficient than interpreting GDL. Not always, but frequently. Moreover, as we shall see, it facilitates the discovery of game structure that can dramatically alter the complexity of playing many of these games. The details of using Propnets to play games are somewhat tedious, and I'm not going to try to go through them all here. If you want to learn more about this, you should read the notes. In this segment, I'm simply going to summarize some of the main issues and the benefits of using Propnets during gameplay. And in the next segment, I'll explore how Propnets can be used offline to restructure games in dramatic ways. Consider a simple variation on the max score subroutine that we saw earlier. The subroutine takes a game description as argument, explores the entire game tree, and returns true if and only if the player has a forced win in the specified game. Let's consider two implementations. The first, called GenWinnerP, uses a GDL description of a game. And the second, called PropWinnerP, uses a propnet. In order to compare the two, let's consider two versions of tic-tac-toe. The first is just our usual encoding in GDL. The second, which is called TTT ground, is also a GDL encoding, but with all variables replaced by ground terms. I'm including this case to see whether the performance using Propnets is due to the elimination of variables or whether it's due to other factors. Now let's look at the results. In my experiment, I first applied GenWinnerP to tic-tac-toe to get a baseline. Sure enough, explored 5,478 states, all 5,478 states in the game tree. Took approximately 130 seconds. And used 142 megabytes of memory. Now that's a little slow, but this was run some time ago on a relatively slow computer. Next, I applied GenWinnerP to TTT ground to see whether the elimination of variables would help. In fact, things got worse. Though the program used less memory, the runtime increased to almost 600 seconds. That's 10 minutes. Actually, it's not at all surprising. By eliminating variables and grounding things out, we increase the number of rules that must be checked, and this increases the runtime. Finally, I used the propositional net program PropWinnerP on the propositional net description TTT Propnet. It explored the same 5,478 states, but this time the runtime decreased to just over 10 seconds, and the memory usage dropped to under 6 megabytes. I think that's a significant saving. But guess what? We can do even better. PropWinnerP still processes Propnets interpretatively. It does not have to be done this way, but that's what it does. We could also represent the state of the Propnet as a list of values or as a bit vector. And we can convert the Propnet in its interpreter to special purpose code to process these representations of state in performing the usual game analysis operations. This translation can be done entirely automatically. Moreover, we can then compile the resulting programs to get even better speed. Here, for example, is an implementation of tic-tac-toe in which we represent the state of the game as a list of 29 Boolean values. That's 1 bit for X, 1 bit for O, and 1 bit for blank in each of the 9 cells, together with 1 bit for controlled by white and 1 bit for controlled by black. Okay, obviously we can do even better by exploiting some mutual exclusions. For example, it's not possible for both white and black to have control at the same time. So we really need just 1 bit for control rather than 2. But the translation from GDL in this way is easy, and as we'll see, we can still get plenty of benefit. Okay, now, given this representation of state, we can define operations for testing states and updating states and so forth. For example, we can determine whether there's an X in cell 1,1 by taking the 0th component of our list of values. We can determine whether there's an O in cell 1,1 by taking the first component. We can compute update in similar fashion. If white does mark 1, 1, and there's a blank in cell 1, 1, then there will be a X in cell 1, 1 after the action is done. Symmetrically, there will be an O if black does mark 1, 1. And if the cell is empty and white and black do not do mark 1, 1, then a cell will remain blank in the next state, and so forth. Now, by using propositional bit vectors in place of lists of booleans, we can do even better. Here I've defined an initial bit vector, 29 bits long, and we can then implement our subroutines by performing bit operations on these vectors. Doing things this way allows us to compute the entire state update in a single operation rather than operations for each proposition, and thereby achieves even greater efficiency. Okay, so here are the results. Same as before, 130 seconds for gen winner P on the GDL description. Just over 10 seconds for prop winner P, that's the interpreted version, on the corresponding propnet for tic-tac-toe. Using the list of values approach and compiling the resulting code, we see that the time drops to under a second, and the memory usage drops to just 3.5 megabytes. And in fact, this memory usage can be made even lower still. Moreover, moving to propositional bit vectors saves us even more. We're down to just 234 milliseconds and only 64 bytes of memory. It's a lot better than the interpreted GDL. Now that's pretty impressive, if you ask me. We're down to we can play 4 games in 1 second on this relatively slow machine. However, it's in principle possible to do even better yet. One idea is to use so-called field programmable gate arrays, FPGAs. These are runtime programmable arrays of hardware gates. Given the structure of propnets, it's possible to use FPGAs for game tree search. Now, although nobody's yet done this experiment, it seems likely that so doing could lead to further speeds up of an order of magnitude or more.